Hello everyone. First of all, before I begin, I'd like to extend my apologies to everyone for not being able to be with you in person today. I had some passport difficulties and so I wasn't able to take my flight, but I still would like to discuss my paper with you, and so that's why I made this movie. And before I begin, I'd really also like to extend my warmest gratitude to Robbie for lending me a little bit of his time to make this possible today. So let's begin. My name is Ned Dimitrov, and today I'll talk to you about some work that I did with Greg Plaxton, my advisor at the University of Texas at Austin. In this work, we'll analyze a class of games. The class of games which we analyze are called Buyer-Supplier games. A Buyer-Supplier game is a type of game that can be derived from any combinatorial minimization problem. In fact, Buyer-Supplier games are also a subset of another class of games called assignment games. And specifically, we're going to analyze the core of Buyer-Supplier games. The core is a game-theoretic solution concept, sort of similar to Nash equilibrium, which I'll also introduce later in the talk. The main purpose of the talk, and the thing that I would really like you to take away, if you had to take only one thing from this talk, is the introduction of the focus point price. The focus point price is a game-theoretic solution or game-theoretic notion that's very similar to the price of anarchy, and again we'll introduce it carefully later in the talk. The main results of the paper are as follows. We basically show that optimizing linear functions over the core of Buyer-Supplier games is as difficult as solving the original minimization problem from which the Buyer-Supplier game was derived. In specific, we show two results. First, we show that if the original minimization problem is solvable in polynomial time, then we can optimize linear functions over the core in polynomial time. Second, we show that if the original minimization problem is not solvable in polynomial time, then even testing core membership is not possible in polynomial time. And in the talk today, we'll focus on a specific application. We'll show how to solve the focus point price in Buyer-Supplier games in a particular setting. And again, you'll see the specifics of that as we get there. So let's begin by having a more thorough introduction to Buyer-Supplier games. First of all, what is a game? To define a game, I really have to define three things. First, a set of players. Second, a set of strategies for each player. And third, a set of utility functions, such that given the strategies chosen by the players, I can know what utility each player derives from that set of strategies. And here is a generic combinatorial minimization problem. It looks like this. We have a set of C of elements, which are the set of elements over which we're going to try to optimize. We have a feasibility function P, which says which subsets of C are feasible or good subsets and which are not. And then we have the function F, which is actually the function we're trying to minimize. So in general, the minimization problem tries to find feasible subsets of C such that they minimize the function F. So we're going to take this combinatorial minimization problem and turn it into a game. So here's what the combinatorial minimization problem looked like. And now I have to describe to you how to create a game from it. So to do this, I'm going to give you a set of players, a set of strategies, and a set of utilities. Okay, so the players for the game are going to be as follows. For each element of C, we're going to associate a unique player that we call a supplier player. So the elements of C are going to be the players that we call suppliers. Then we're going to introduce a unique player that we call the buyer. And the buyer and the suppliers are going to be involved in a purchasing transaction. That's why the strategies are as follows. Each supplier simply chooses a non-negative real number bid, and the buyer chooses a subset of the suppliers from which to do a purchasing transaction. So far, I still haven't discussed how the feasibility function P or the function F go into defining the buyer-supplier game. So they go into defining the utilities. To define the utilities completely, we're going to do the following. We're going to take the function f and we're going to decompose it into two parts. First, the first part is going to be the internal cost of the buyer for choosing this particular set of suppliers. So this can sort of capture preferences that the buyer has for some sets of suppliers over others. Second, we're going to have an internal cost for each supplier. This internal cost basically captures the cost of the supplier for being chosen to the buyer. Since the supplier has to provide some services, this is sort of a natural thing to include in our model. To make the model even more realistic, we're going to add a maximum amount of money M that the buyer is allowed to spend to purchase a feasible set of suppliers. And the utilities are ultimately determined by the purchasing transaction that happens between the buyer and the suppliers. So far I've described to you in a very abstract fashion how to start with a combinatorial minimization problem and get a buyer-supplier game. But let's look at two specific examples to make this more concrete. First, consider the minimum spanning tree minimization problem. In this problem, we're trying to, the set of elements which we're trying to optimize over is the set of edges in a graph. The feasibility function basically asks, do the edges span the graph? The function that we're trying to optimize is simply the sum of the weights of the edges. So we start with this combinatorial minimization problem, and we want to turn it into a buyer-supplier game. So the first thing that we need to do is decompose the function f into two parts, an internal cost to the buyer and an internal cost to each of the suppliers. So this decomposition is going to be very simple. The internal cost of the buyer will be 0, and the internal cost to each of the suppliers will be equal to the weight of the edge for each supplier. So let's continue and fully define the game. So the set of players for the game are going to be as follows. We'll simply have a unique supplier player associated with each edge of the graph. And each of these supplier players has an internal usage cost for being a member of the buyer's chosen set. We also have the unique buyer player, represented by this icon here, that's trying to buy a spanning tree of the graph, or a set of edges which span the graph, is trying to spend the minimum amount of money to do so. And the buyer cannot spend more than M for purchasing this spanning graph. So the strategy sets, again, are the strategy sets in the purchasing transaction. Each supplier submits a real number bid, and the buyer chooses a subset of the suppliers from which to make a purchase. The utility functions are then determined by the result of the purchasing transaction. So let's take a look at a slightly more complicated combinatorial minimization problem and turn that into a buyer-supplier game. So here is the facility location problem. In the facility location problem, we'll have a company, you can think of that as the buyer, that has some customers throughout the graph. The customers in this picture are represented by the green dots. So the company must deliver products to each of its customers, and to deliver these products, the company must build facilities in the cities that are in the graph. So the cities here are represented by these pictures. Notice that a customer need not be in a city, and a city need not have a customer. So let's define the minimization problem in terms of what we looked at earlier. So the set of things that we're trying to optimize over is the set of cities. We're basically trying to choose in what city we should locate a factory such that we can supply all of our customers. The feasibility function is very simple here. It basically says, can we supply all of the customers with the factories, with the locations that we've chosen? And the function f that we're trying to minimize is the sum of the service cost of running trucks between our factories and the customers, plus the sum of the opening costs of opening each of the factories in our chosen cities. So we're going to decompose the function f as follows. We're going to have a buyer internal cost, and this cost will basically equal the cost of running trucks between our chosen factories and our customers. And then we're going to have a supplier internal cost. And these costs represent the internal cost of the cities for hosting a factory. For example, there may be some pollution damage, the company uses the city's roads, etc. So the city has some internal costs for hosting a factory. So let's go on to define the game. For the players of the game, we have one supplier player for each city and a unique buyer player. The strategies are as before, they're real number bids, and the buyer chooses a set of cities in which to purchase a factory. But the utilities now have the internal cost which we discussed. The buyer has an internal cost associated with running the trucks, and each supplier city has an internal cost associated with hosting a factory. But ultimately the utilities are determined by the purchasing transaction. Okay, so I hope now you have a pretty good understanding of how to take a combinatorial minimization problem and turn it into a game. So let's start analyzing the game. And to do this, we have to introduce the game theoretic solution concept of the core. So here is a game with outcomes. But we'd like to do more than just describe a game, strategy sets, and utilities. We'd actually like to predict what happens if players actually play this game. And that is what a solution concept does. A game theoretic solution concept predicts which of the outcomes of the game will actually happen when players play in real life. So one solution concept that you're all familiar with is the Nash equilibrium solution concept. And this solution concept basically identifies outcomes in which no player has incentive to unilaterally deviate from that outcome. But there are many other solution concepts, and today I'll introduce you to one such one called the core. So informally, you can think of the core as a generalization of the Nash equilibrium solution concept. So in the Nash equilibrium, no individual player had incentive to deviate, while in the core, no subset of players has incentive to deviate. So let's be more explicit about this. Suppose that we have a set of players P and a utility function for each player. Then we'll say that a payoff vector is not in the core. If there exists a set A, this will be the set that has incentive to deviate, such that that set has a particular strategy S, such that for all strategies of the remaining players, the players in A each get a higher utility from following S than the payoff vector pi gives them. So that's how we know that a payoff vector is not in the core, because we've identified a set that has incentive to unilaterally deviate. Okay, so let's go on to the first real contribution of this paper, that's the focus point price. So we saw this picture just a moment earlier. We had a game with outcomes and a solution concept. But most of us are computer scientists and we like to do computation. And to do this, we have to throw another thing into the mix. We throw in an objective function. This objective function basically tells us which outcomes are preferable to others. And so in computational game theory, we do things such as mechanism design, where we try to play around with the definition of the game so that a particularly desirable outcome is included in the solution concept. Other things that we study are the price of anarchy, which basically tries to determine how much we lose from the fact that we play a game instead of having a dictator. In other words, we're looking at the difference between the best overall outcome and the best outcome that's inside of the solution concept. In this paper, we introduced the focus point price. And in specific, the focus point price is the difference between the best outcome in the solution concept and the worst outcome in the solution concept. This is sort of answers the following question. Suppose that we cannot change this game. We're stuck playing this game and we will come out in some sort of equilibrium. But we perhaps have a little bit of flexibility in which equilibrium comes out. We can sort of do some advertising to have players focus on a particular equilibrium and play that one. So focus point price really answers the question, if we're constrained to play an equilibrium, how much are we willing to pay to choose which equilibrium is played? And similar to the price of anarchy, we're sort of looking at a worst case thing. That's why we're looking at the difference between the best equilibrium outcome and the worst equilibrium outcome. Okay, so let's take a look at some related work to our paper. First of all, buyer-supplier games have been studied for a long time. For example, Shapley and Shubik characterized the core of buyer-supplier games. There have also been some more recent papers studying the core of buyer-supplier games. For example, these papers relate the core to auctions. They show that under some conditions the core is in a lattice. But one of the primary differences between our work and these papers is that they are primarily concerned with characterization of the core, while we are primarily concerned with optimizing over the core. There's also been some recent papers studying the frugality of auction mechanisms. I'd like to just explain how frugality is different from focus point price. Frugality is very similar in some sense to the price of anarchy because it studies how much you lose from the fact that you purchase something at an auction instead of being able to buy it for the minimum possible price. While focus point price studies an entirely different question, which is, imagine that you're stuck playing this game, but there could be different possible equilibrium outcomes. How much are you willing to pay for which equilibrium outcome gets chosen? So another major difference between our paper and these papers is that they're primarily concerned with the Nash equilibrium solution concept while we study the core. Perhaps the closest paper in the literature to our own is a paper by Fagel and Kern. They, in fact, study optimization over the core of buyer-supplier games, and they show how under some conditions you can have a greedy algorithm for optimizing over the core. Our paper is different from the paper of Fagel and Kern in that first we present a different algorithm for optimizing over the core, and second, our algorithm is more widely applicable because it's based on the Ellipsoid method, and in general it's applicable to all buyer-supplier games, not just a subset of them. And thirdly, or lastly, buyer-supplier games isn't the only way of changing a combinatorial minimization problem into a game. So there's been at least a couple of papers that study an alternate transformation from combinatorial optimization to games. And they as well study separation and optimization over the core in this alternate transformation. Okay, so let's get to actually looking at optimization over the core and a specific example of focus point price. But before we can optimize over the core, we have to have a characterization of the core. As I mentioned earlier, the core was characterized by Shapley and Shubik a long time ago. So for the rest of the paper, we're going to focus on the minimum spanning tree buyer-supplier game. However, everything which I show you in the slides very easily generalizes to all buyer-supplier games. So simply because we use the minimum spanning tree function doesn't really lose generality. It's just convenient because we all know what it means. So here's the characterization of the core, and let's interpret it for a second. This first equation says that the payoff that each player must get must be bigger than or equal to 0 for all players. Now, this is simply an individual rationality constraint saying that no player is going to play a game where they know that they're going to get a negative payoff. The second constraint looks like this. On the left-hand side, we basically have a sum of payoffs to a particular set of edges. And on the right-hand side, we basically have how much those set of edges contribute to lowering the minimum spanning tree cost. So this is the absolute minimum spanning tree cost, and this is the minimum spanning tree cost if we're not allowed to use the edges in A. So this constraint says that the set of edges in A cannot demand more payment in total than they together bring to lowering the minimum spanning tree cost. This is sort of a demand limiting constraint, saying that a set of edges cannot demand more than their marginal contribution to the minimum spanning tree cost. The final constraint is a very simple one. It basically makes sure that money is not created or destroyed during the purchasing transaction. So it simply determines what the payoff to the buyer must be given the payoffs of all of the suppliers. Okay, but as I said, we have a game, we have a characterization of a solution concept, but we need an objective function to really study focus point price. So the objective function that we're going to study is the amount of money that the buyer gets. So let's figure out what's the maximum possible amount of money that the buyer can get. Consider this a counting constraint. Notice that when we set the pi values to all edges to 0, the first two constraints are feasible. And the accounting constraint basically says that the buyer gets this amount of money. So this is the absolute maximum amount of money that the buyer can get. But we're interested in the difference between the maximum amount of money that the buyer can get and the minimum amount of money that the buyer can get. So let's figure out what's the minimum amount of money that the buyer can get from this purchasing transaction. In other words, we're going to try to maximize this quantity right here. Okay, so now we have our optimization problem that solves the focus point price for this particular minimum spanning tree buyer-supplier game. So as you can see, what I have on this slide here is a linear program, but it's not a regular linear program because it actually has an exponential number of constraints. We can't even write down this linear program in a polynomial time. So we must use some other method to find its solution. We can't simply use the simplex method or anything that really iterates over the inequalities of the program. So what we'll do is use the ellipsoid method, which is really the only method that I know of solving exponentially sized linear programs. The way that it works is as follows. You start with this feasible region and you put it in a gigantic ellipsoid. Then you query the centroid of the ellipsoid and you ask, is this centroid feasible? And if it is feasible, then we'll say we're done. And if it's not, we'll find a separating hyperplane between the centroid and the feasible region. Then we'll use that separating hyperplane to update the ellipsoid to a new ellipsoid of geometrically smaller volume. So as we iterate this, we every time get a geometrically smaller ellipsoid until very quickly we either find a feasible point or we know that no feasible point exists because the volume of the ellipsoid is so tiny. And it's very easy to turn finding the ability to find feasible points into the ability to optimize just by sort of doing a binary search on the objective function value. So that's exactly what we're going to do in our problem. We're going to sort of be able to find these separating hyperplanes. So what that is called is being able to do that is called having a separation oracle for these exponentially many constraints. So given a vector pi, we're going to be able to tell if pi satisfies these exponentially many constraints, and if it doesn't satisfy it, we'll be able to output a particular inequality that's not satisfied. So here's the basic idea of our separation oracle. We're basically going to solve the minimum spanning tree problem twice. First, we're going to solve it with the original weights, and then we're going to solve it with increased weights where we added the demands. And if the minimum spanning tree solution changes, then we know that some set of edges must be demanding more than what they should be getting paid. So let's be more explicit about what the separation oracle does. First of all, the individual rationality and the accounting constraints, there are only polynomially many of them, so we can just directly check them. Then we're going to compute the minimum spanning tree T, and we're just going to check that all edges outside the minimum spanning tree aren't demanding any payments because the demand limit constraint for them, for those individual edges, forces the demands to be 0. Then, as I said, we're going to increase the weights and solve for a new minimum spanning tree. We'll compare the old and new minimum spanning trees, and if we're different, we're going to output a particular demand limit constraint. So really, to prove the correctness for this, I have to prove two lemmas. I have to show that if the separation oracle returns an inequality on input pi, then pi violates the returned inequality. And I also have to show that if pi violates an inequality, then the separation oracle will return some inequality. Okay, so let's see what we've talked about today. We've talked about buyer-supplier games. I introduced those to you. I introduced you to the core. Then I introduced you to focus point price, which was the one thing that I would like you to remember if you remembered one thing from the talk. I discussed then a very specific example of how we can solve the focus point price problem in a particular buyer-supplier game. However, in the paper, you're going to be able to see the fully general results. In other words, you'll find also the matching negative result that shows that if the original minimization problem is not solvable in polynomial time, then you can't test core membership in polynomial time. Second, right, so that's what I said. You'll find these impossibility results. You'll also find the combinatorial algorithm for optimizing or for solving the focus point price in the minimum spanning tree buyer-supplier game. As I said, minimum spanning tree is a problem that we're all comfortable with, and that's why I used it in the talk. But in fact, you can optimize over the core of the minimum spanning tree buyer-supplier game using Fagel and Kern's greedy algorithm. However, there are other problems that are just as simple as minimum spanning tree, for example, shortest path, that we know of no other method of optimizing over the core of the corresponding buyer-supplier game except using the ellipsoid method, which I described to you today. So here are some future directions to follow in this area. First of all, I would like to see focus point price applied to other situations. Remember that all you need to apply focus point price is a game theoretic solution concept, and an objective function. The second thing I'd like to see is sort of a similar analysis, but when we add multiple buyers into the picture. So everything that we've talked about today involves just one buyer. So it would be interesting to see how we can optimize over the core if we have multiple buyers. So this changes a buyer-supplier game into a more general set of games, which I mentioned earlier, called assignment games. I'd also like to see if we can find some combinatorial algorithms for optimizing over the core. For example, as I mentioned, there's no other method for us to optimize over the core of the shortest path buyer-supplier game except the ellipsoid method we talked about today. Is there a combinatorial algorithm for doing this? I'm not sure. I've thought about it for a little bit, but I couldn't come up with anything. Finally, I'd like to see if we can do this optimization over the core under some uncertainty. Everything I talked to you about today involved knowing the internal costs of the buyer, knowing the internal costs of the suppliers, but suppose that we just have a probability distribution about over them, or we just know the ranges in which they are. Can we do something in that case? So those are all of the future directions that I'd like to talk about today. Thank you very much for listening, and again, I'm sorry I couldn't be there. Thank you to Robbie, and please email me if you have any questions.